Good evening, everyone. This is Fatin Samir, and today I'll be explaining my passive design project, starting with a table of content. I'll be talking about introduction, aims and objectives, site analysis, concept, design strategies, IES simulations. What is a passive house? Passive design house refers to a type of building design that emphasizes energy efficiency and comfort by utilizing the natural resources available in the surrounding environment. And the concept of passive design is back to 1970s as a response to the global energy crisis and the need of more sustainable and environmentally friendly building practice. And it's also a building design approach that leverages the climate and natural elements to maintain a comfortable indoor temperature while reducing or eliminating the need of use mechanical systems for heating or cooling. And it focuses into two main factors, climate and comfort. The objective of this research is to develop a passive design country house with the aim of achieving the following objectives: incorporating sustainable elements and strategies throughout the house design, construction and operation to minimize environmental impact and promote long-term sustainability. Designing a house that significantly reduces the energy consumption through the implementation of energy-efficient strategies and technologies. Implement passive heating and cooling strategies to the house, ensuring optimal comfort level in various areas of the house, taking into consideration factors such as indoor air quality, thermal comfort, and visual appeal to create a pleasant and enjoyable living environment. By addressing these points, the research aims to showcase the successful integration of passive design principles, sustainability measures, and enhanced comfort within the country house. My project is located in East London in an area called Swardstone, which is near to River Lee. Swardstone has a historical connection to farming and the nature reserve that provide a unique opportunity to observe a wide variety of plant and animals. Project site is surrounded by two main roads. One is the London Orbital Motorway, located to the north of the site, and the other one is Swardstone Road, which forms the eastern boundary. Additionally, there is a local road called Mile Lane that directly connects the site from north, making it easily accessible and convenient. This spatial location of our site brings several advantages, like presence of these two roads creates a sense of privacy by keeping the house away from noise and busy areas. The figure showcases significant geographic landmarks and features surrounding the site. Gunpowder Park is from the north and Epping Forest to the east, and it's 3.5 kilometers away from the site. Also, the Woodland Gilwell Park is away 900 meters from the site. The Durrant Park and Bounder's End are notable public features in the area. Attraction enhance the desirability of our site as an ideal location for a country house, offering an enjoyable countryside experience alongside a wealth of neighboring attraction. In this diagram, it highlights the fact that our site is surrounded by a wide range of important services. London experiences a moderate annual temperature range. Summers are typically mild to warm, with average high temperature ranging from 20 to 25. Winters are cool, with average high temperature ranging from 7 to 10 Celsius, showing in the figure, and the city rarely experiences extreme hot or extreme cold temperature. So London annual temperature enables the implementation of passive strategies to create energy-efficient building. Talking about sun path analysis, to the left, its chart focuses on the winter-spring periods, and the summer are to the right. During the summer-fall period, temperature exceeds the comfort level, which is 24 Celsius, necessitating the use of shaded outdoor areas on southern side to mitigate the discomfort caused by excessive heat. During summer-fall period, 364 hours of sun exposure, while in the winter-spring period, the sun exposure is only 84 hours, so we need to introduce the sun during winters to mitigate the comfort levels. Moving to the windrows analysis, sites experience a diverse range of wind direction due to the London geographical location and urban environment. The prevailing wind is coming often from south-southwest, and the figure illustrates longer or thicker segments in the south and southwest direction, indicating a higher frequency of wind from those sectors. The north and northeast direction also have relatively wind, but the lower frequencies, while right figure shows that the wind speed is around 16 miles per second. So when it comes to design concept, climate and site analysis should be considered to maximize energy efficiency and comfort. Here are some of the best passive design strategies that I will be considered. 1. Orientation and layout. Optimize the orientation to make the most of natural daylight and solar heat gain. 2. Natural ventilation. Design the house to facilitate natural ventilation and airflow. Natural light. Maximize natural light penetration by incorporating skylight, light wells, and light tubes. 4. Thermal mass and insulation. Incorporate thermal mass materials and ensure proper insulation throughout the building envelope. 5. Windows and glazing. Windows with low UV and higher solar heat gain coefficients. Double or triple glazing combined with low emissivity coating can enhance thermal performance. So after implementing all of these ideas, we will get a passive design house. So after all these studies, I did well-structured bubble diagram that showcases the optimal placement of key spaces. As shown, the goal was to create a passive house, consist of living rooms, bedrooms. So family living is consist of 2 rooms, one in the ground floor and one in the first floor, and 1 dining room. 1 living room for the guest in the guest house. On the other hand, the placement of the bedroom was preferred in the hidden, quiet areas. So the 4 bedrooms, 3 for children in the ground floor and 1 master bedroom in the first floor. While in the guest house, 1 master bedroom is there. So this thoughtful arrangement adheres closely to the BREEAM codes and regulation, ensuring compliance with sustainable building practices. So moving to the massing concept, the living rooms are positioned toward the north, takes advantage of ambient sunlight, while also providing a breathtaking view of the river from the western side. While the guest house is placed in a place providing a privacy in the private accesses and also still offering a view toward the river from the west, and both of them are sharing the same courtyard together. So still it's connected house. And to mitigate the summer heat, the farm area has been thoughtfully situated to the south, casting shade over the house during the warmer months. So the concept of an infinity house has been implemented seamlessly, connecting the interior and the exterior spacing, creating a sense of endless opening. While use movable elements to achieve the passive cooling and heating strategies by implementing shaded courtyard strategy in my design that can prevent excessive heat gain during summer while allowing for ample sun warmer in winters. Let's check how. An upper corridor was introduced, functioning as a shading device and also defining a central courtyard. This integration not only enhanced the overall design aesthetic but also cooperated to harmonize indoor and outdoor transition. The implementation of dynamic shading device, which could be employed in corridors to establish a shaded courtyard during summer months and penetrate the sunlight in winters. In designing my country house, I have carefully integrated various strategies to maximize energy efficiency and improve indoor comfort. Number 1, thermal mass. 2, orientation and natural ventilation. 3, sun space and efficient glazing to reach the passive heating and cooling house. And to do so, IESVE software is used to simulate different cases that will be used to improve the indoor comfort. Starting with the thermal mass, it's incorporating a thermal mass material such as a blockwork cavity wall to absorb and store heat during the day and release it at night gradually, as well as using insulation because the well-insulated house prevent heat loss. Use high-quality insulation materials in walls, roof, floors, and also the windows. Minimize thermal bridging and maintain the comfortable indoor. The base case is showing default construction materials utilized in London without any modification. After simulating in IES, the table is showing the total energy consumption during the year, and it's 8.96 megawatt per hour. And here is the material of the base case and its U value. Upon reviewing these materials, the passive model considered the green guideline rating, determining the optimal house material. As a result, it was enhanced to achieve an A+ material rating according to BREEAM. And for the external walls, employing blockwork cavity wall was significantly lower the U value from 0.25 to 0.15. So this enhancement aims to improve the efficiency and effectiveness of heating and cooling systems. While the implementation of a flat roof warm deck considerably reduced the U value from 0.18 to 0.11. And lastly, double window with argon gas has been selected as the optimal choice, and this selection resulted in decreasing the U value to 1.6. So the passive model demonstrates a remarkable achievement of approximately 23.4% energy saving throughout the year. Moving to winter and summer period, here is a comparative analysis of space heating and cooling load between passive model and the base case. And it's showing a drop in the space heating and cooling during the winter and Summer. Second strategy is natural ventilation and orientation. The figure highlights that the design of the house has been thoughtfully developed the optimal natural ventilation by integrating operable windows and vent. Windows have been positioned toward the south, while open courtyard facilitate the entry of refreshing breeze into the house, enhancing the overall cooling effect in summer. While in winter, the courtyard is enclosed by movable louver, providing protection from cold winds and minimizing the heat loss. And the intentional design adjustment helps to maintain a cozy, warm living environment during cooler periods. In this figure is showing the result of CFD external simulation conducts on the house, both before and after the addition of the courtyard corridor. It's showing enhancement of airflow underneath the corridors. This modification contributes to improved ventilation and circulation, which can positively influence the overall thermal comfort and indoor air quality within the house. So in this figures, the courtyard enhances the air quality within the living spaces by placing windows in both sides, south and north orientation. A cross ventilation effect is achieved, and the air velocity within the window reach approximately 0.07 meter per second, creating a comfortable environment within the living room. In terms of the orientation, a 3 orientation was examined: north and 30 degree to the north and minus 30 degree to the north. And we found that the north is the efficient orientation to place our house, and it drops the energy to 7.5 megawatt per hour, which is the best solution for the house. Moving to the last strategy used, sun space and efficient glazing. A sun space was placed in a guest house, and it plays a significant role in passive cooling and heating of the building. So the sun space mechanism is the glass allowed sunlight to enter and warm the space. Then the solar heat gain can be utilized to supplement the heating need to the adjacent living area. So this strategy can capture solar radiation for heating purposes in winters, while in summer warm air can be vented out during hot weathers. So after that, the IES simulation has been done to test this strategy. And the result shows that the total energy consumption decreased by approximately 18.85% from its initial value, and the final value is 7.27 megawatt per hour. And the space heating loads also reduced 3.17 per year, and it's around 35.85% saving. While in terms of efficient glazing, this table illustrates a triple window glazing configuration has been implemented as part of the overall design, which reduced the U value to 1.106, and the reduction in heating and cooling load is noticed. This finding underscores the efficiency of the passive strategy. Finally, by effectively incorporating passive design principle, sustainability measures, and improved comfort, and we aim to set an example of sustainable practice, showcasing how architecture, energy efficiency, and the human well-being can harmoniously coexist.